Hello, everyone. Hello, hello. I am running late today. Can you believe it? Me running late. This is so unlike me. This is so unlike me to be running late all the freaking time. Oh, goodness. So, hopefully, let me check and see if I'm live everywhere. Woohoo! Thank you for your patience while I was getting everything together and stuff. This has been pretty nutty. It's always a challenge for me because when I go through and when I go through and I'm putting together a show, suffering from chaos, maybe. Yeah, isn't it? Hello. So when I'm going through and like putting together a show, it's always pretty interesting because I tend to get the topic like the night before because my polls can kind of run. Hello. My polls can kind of run they kind of run long sometimes. This was about 650 people voted on this, and it was pretty close between ducks and chaos theory. So chaos theory won out. I won't be getting too much into heavy mathematics with this one because the mathematics are, oh my gosh, freaking just mind-blowing type of mathematics. So I wanted to talk a little bit about, I do spend a lot of time going through, and I've been up since about 7 this morning, going through compiling the show together, trying to get as many resources as I can. So as much as I'm a fan of chaos theory from Dr. Ian Malcolm and and life finds a way, as much as I'm all about that, my knowledge about chaos theory, this isn't what I'm trying to say. I love doing shows like this because it challenges me to go and dive down and get my hands on really good resources and go through and learn something new. And I got to learn some things with chaos theory. So thank you guys for voting for this particular topic, because it's just really, really freaking cool. I'm not getting into the heavy math of this, more of like what it is, what qualifies something in order for you to see chaos exhibited in it, what you got to do with that. Hello, how that works. So let's go ahead and get started. Yay! Okie dokie. So hello guys, I'm so glad you're here and hanging with me. Let me post a couple things here and see if we can't get some people going. Sometimes people need extra alarms like wakey, 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 eggs and bakey. Scientists. Yes. So this is going to be one of those fun videos where I talk about chaos theory and where it's going through, and hopefully, I'm always a fan of chaos because that seems to happen nearly every single time I get on one of these shows. So hello everyone. So chaos theory is pretty freaking cray, man. It's nuts to a degree, but it's a lot of fun. So what I'm going to talk about hello, Andy. Hello, everyone. Hello, Axel. So I'm going to talk about is chaos theory. What is it? Where do we see it? How does it have an effect on things? And how do scientists use it? So we're going to dig into a lot of what is it, because some people only know chaos theory from life finds a way, you know. I kind of wish I kind of feel like I should talk more often like Jeff Goldblum, because I just really like the way that he says things, you know. So, I didn't change my camera. This is what we're talking about today, right here. What is it? Where do we see it? How does it have an effect on things? And how do scientists use it? You might say it's chaotic. You know, it's really funny. It's just, there are specific things that have to happen in order for a system to be chaotic, which is actually kind of cool. So what I'm going to talk about, so let's go ahead and dive into some of this. I know y'all hear my mouse clicks, but just know it's just me running everything, which is fun. So we have to go back to the very, very, very beginning, where we see a gentleman by the name of Edward Lorenz. And in 1961, he noticed that his computer gave him a very different answer from what he was expecting when he started at the very beginning of his calculations. Well, what he found is that that's where it took a shortcut and started near the midpoint. Now, when you're thinking about these little shortcuts, especially with mathematics, you wouldn't really think it would have mattered, because the differences in this case were so very small that it should have been negligible. But as a result, he discovered that this was highly dependent on the starting conditions. So the final result of the calculation was so different from what he expected, even though there was a slight change. Well, that slight change he started with was this number, 0.506127. So that was the initial number that he started with these particular calculations, and it had to do with weather forecasting. Now, his shortcut is something, if you're familiar at all with Excel, this will rip your hair out, especially if you're trying to get to precision. It rounded the number to 0.506. Well, that rounding shouldn't have made such a big difference, but it actually did. The calculations in this case had to do with the weather, and the rounding of that error should not have made such a small difference. But the thing is, the results of the two calculations were totally different. So this practical kind of conclusion from this particular discovery is that long-range weather forecasting kind of doomed to failure. You can't do long-range weather forecasting for this reason. And this isn't because we can't necessarily get the best measurements, but it's more like the uncertainty principle of quantum mechanics. You know, the more you know about one particular thing, you know, the more you know about the momentum, the less you know about where it is. And the more you know about where it is, the less you know about the momentum. Well, this is where we get into how little things move, and little things move all kinds of weird ways. But the thing is, we have distinct limits as to how far off we can predict events with a strong degree of certainty. This will help you rip your hair out. I'll take it. Oh, Mel, I can feel the fractals on their way, all from rounding a number. Yes. Oh, you like my new specs? Yes, guys, I'm looking better. You see what I did there? With my new specs, my new glasses. I really did need some new ones. My old ones were off, I think, by 0.5. But I liked the frames of my old ones. That's why I kept them around. So these are kind of the things we got to keep in mind. On a related note, especially in computer simulations, I used to do research in computational chemistry, and I worked with the LPA2 receptor. And if you're familiar at all with molecular orbital environment, MOE, also known as MO, if you haven't learned about it, you probably will if you take organic chemistry at university. I had our 3D model of the LPA2 receptor, and I had known ligands that I knew fit in there and were very effective at reducing. They actually reduced receptor activity. So they were antagonists. And we had all the data knowing that these particular ones were supposed to fit in this receptor. But the software, being as it is, kept throwing it out as thermodynamically unfavorable. Why was it doing this? I spent so much time trying to figure out how it was that these particular ligands, these particular compounds were not fitting in this receptor. Well, turns out you could put in, the structure, but that software randomly assigns stereochemistry. I did not define the stereochemistry in that, and thus I got vastly different results, and it said, this would never fit in there. It's not going to work. Well, guess what? When I assigned the stereochemistry, it was the complete opposite of what the software was assigning it. It was assigning it a particular ligand, which we had tested, that did not work at all on this receptor. So this one small change caused me to have so much grief over the course of a week because we had not assigned the stereochemistry. You wouldn't think it would matter that much, but apparently if you didn't assign the stereochemistry for this particular molecule, it was going to throw it out and say, this is not thermodynamically favorable. Like, yes, it is. We have wet lab data. We have all the data that shows that, yes, this works. What are you doing, computer? Well, that's where you kind of get into the more information that you have, particularly about a situation, the more you can predict what happens. And we're going to talk about that today a little bit with chaos theory. But that's kind of like some personal information for that, what I've been through. So when we're looking at something like that with my example, so when you're looking at every single event that happens, there's different types of teeny tiny uncertainties that can multiply over a period of time. Now, this can go into what we call a cascading upward into unpredictability. So the more small uncertainties you have, the longer the time passes, you're going to have more unpredictability. Now, if we look at people are complex systems, both physically and mentally. So when we start out with our birth and our development as a child, this in a way determines how it is that we are going to find ourselves as adults. You can have things that happen to you when you're young that's going to have an effect on you much later in life. Because we don't enter life as a blank state, we kind of already enter life with pre-established desires and traits. We see this in our genetic code. So we do have, in a way, some particular things that are kind of put into place, especially with us when we're talking about our genes, about certain genes being expressed in us. These are all going to play a factor. These little teeny tiny changes in genetic code are going to play a factor in how we develop as people. And so with that said, early part of our lives affect us later on in life. Vaccination is extremely important. There's also some in psychoanalysis that argue we must remember our early childhood if we're to find maturity as adults. And in Jung notes, Jung, 1989, he says the enormous influence which childhood has on the later development of character is what we see. He also says that most neuroses are misdevelopments that have been built up over many years. So you can have small things that happen in the beginning, and then they just go poof, and they turn into larger things. So what does this mean? Essentially, what is this thing called chaos theory? Chaos theory. It is the science of surprise. You got, that's the element of surprise, isn't it? OH. Or AH, the element of surprise. So it's the science of surprise. So how correct is enough? Pi to 100 digits, 1,000 over 9,000? That's a good question. It's hard to know what correct is enough, and it's going to deal entirely on the initial set of conditions. That's where we get into the butterfly effect, which is pretty cool too. So I'm going to bring that up in just a bit. So when we're dealing with the science of surprise, it's unpredictable phenomena. And we kind of compare, when we're looking at chaos theory, we're comparing the predictable with the chaotic. So what exactly does that mean? What does it all mean? Sometimes we can get into an existential crisis reading this stuff. So essentially, chaos theory studies the science of surprise, while most science strives to study the predictable for repetition and understanding how things work. We look at gravity, we look at chemical reactions, we look at certain types of behaviors and phenomena that are repeatable under very specific conditions. And this is linear. We look at PV-nRT, the ideal gas law. So we can use equations like this, and we have expected and repeatable outcomes. But there are still elements within that that are considered unpredictable. So chaos theory looks at this unpredictability, things that are not linear and all of the factors that can influence a thing. It looks at fractal properties and chaotic behaviors in order to study the unexpected. While like scientific laws give us repeatability under specific conditions, chaos theory looks at the things we cannot control, such as turbulence, weather, brain patterns, and brain states. They look at the stock market. You can even look at sports. Recognizing and understanding the expected in nature and society and the unexpected in these systems help give us insight in that the smallest thing we would not normally expect could cause the long term to collapse, even in detriment. The law of entropy, is it essential to chaos theory? I would believe so. If you look at, and because I love thermodynamics. Oh my gosh, I love thermodynamics. It is so awesome. I like quantum too. I don't know enough about quantum, and I'm seriously thinking about taking a class about it. Just for fun. But chaos theory, when you're looking at entropy is the increase of chaos. And so you can have a lot of play between chaos theory and entropy, especially when you take into consideration the ideal gas law and gas particles and molecules and how they all bounce around and stuff. Trajectories is exceptionally important in chaos theory, because that's kind of where they get to the mathematics of that when we get into what we're going to talk about with the pendulum and the pendulum experiment. Let me scroll back a bit. Now, I'm now thinking of Jurassic Park Jeff Goldblum actually knows what she's talking about. I try, and if I'm wrong, I'm wrong. And somebody mentioned about, Wellington mentioned how pi to 100 is 1,000 over 9,000. It's going to depend entirely, I guess, on the sensitivity and the precision of how much accuracy you're going to have, especially in particular calculations. I would think entropy plays a huge role in chaos theory, especially since you can apply chaos theory to thermodynamics. And it's in chaos theory, when they're looking at it, they're looking at very specific systems. And so let's get into a little bit of that. Man, I'm telling you, I've been reading like mathematics stuff like all morning, and I'm sitting here drinking my coffee going, man, this is fascinating. Wow, look at these variables. And I'm sitting here going, man, all the math. So I'm going to show you a little bit of math, so don't freak out. I'm going to show you some math today, but it's not scary math. Sometimes math is scary, but it's not scary math, so it's all right. So when we're talking about chaos theory, used to, before chaos theory was a thing, you would go, okay, do we see something weird? Do we see something that's not linear? Is there something going on? They used to look at two different things. They used to think that chaos, they used to see something and they would assume it's not chaotic, but they would look at how complex it is and if there was any noise involved. So what exactly does that mean? Well, back in the day, science would have to consider erratic and random appearance of behavior in the natural world for two very distinct reasons. Oh, you like my mug? I got this a couple years ago. I thought it was pretty funny since it's October and all, you know. Hey, I just want to look at pretty pictures. That makes my eyes bleed. It'll be all right. You guys got this. It's all right. So science used to have to look at two different things in regard to anything that they thought was erratic or random in appearance of behavior within the natural world. The first thing that they would look at is complexity. And the second thing they would check out is noise. And they're like, all right, what exactly is complexity? Well, it takes into account that there are many degrees of freedom, also known as variables, that are needed in order to pin down the state of a system at a particular time. So if we're looking at a particular system, all right, my coffee cup, all right, if I have weird stuff going on, you know, baristas like to go and they put like the little things inside of your coffee cup that make the different images and stuff like that. They can change those images. And so, and sometimes that image is going to swirl and mess up. Well, the reason for that is you've got to take into consideration all the variables that are involved with making that image and messing up that image. So complexity takes into account those different degrees of freedom, those variables that are needed in order to figure out the state of a system at a particular time, like the temperature of my coffee, the image that's in it, the cream where it's placed in my particular coffee, all of these different things. That's like a snapshot of a second of what's going on with my coffee. But that's just one particular time. Over time, it's going to change. So, so you thought it said Twitch, please. That's funny. Okay, so another thing to look at. You could have a box of gas. You could have a galaxy of stars. The system, because it has so many variables, so many things involved with it, has the strong possibility of showing extremely complicated behavior. Now, the other thing we're talking about was noise. Noise addresses behavior that is influenced by outside and random effects. So you could have temperature fluctuations, mechanical vibrations, you know, so you could have little vibrations as I'm holding this cup here and I'm moving it around. I've got outside noise that are affecting my internal system involving my coffee and my cream and that sort of thing. There's also cooling here. Now, for this reason, if we have noise having an effect on a system, it might show complicated and unpredictable behavior. Chaos theory allows us a third explanation for such complex behavior. Chaos theory is important because it works to explain complicated and apparently random behavior we observe in a system with only a few variables involved that are not really affected by properties of noise. So we can see different things that aren't involved by outside influence that have random and strange patterns. And this is kind of where chaos theory comes in and explains a few things. So let me go back. Can chaos not be applied to any open or organic system, or is that essentially inherent in any open system? Chaos can absolutely be involved in organic and open systems. We look at brain states and brain patterns, decisions that we make. I'm going to talk a little bit. I'm going to talk about a very, very cool example. We go through chaos theory all the time. So we have different things that happen to us that are entirely random, but we can also have random things that happen within us as well. But just about any open system can be subjected to any kind of chaos. Okay, may I suggest quantum chromodynamics for a science episode? Wow, that sounds cool. I think so. I'll show you chaos, man. Says a dude on the internet named Ian. Absolutely right. Lots of dudes on the internet show me chaos all the time. So, Math is not scary. All right. I think I'm caught up on stuff. Shaken, not stirred. All right. Can chaos theory predict the future? Chaos theory looks at the unexpected, but the more you know about the initial conditions at the start, the more you can know about the fate of the particular thing. And I'll get into that with the butterfly effect. But the first thing we need to talk about before we get into that are the different types of terminology. So for instance, fractals. You guys have been looking at this image. These are never-ending patterns. You know, I kind of am reminded of the never-ending story, you know. Oh, goodness. We have these never-ending patterns that tend to be infinitely complex, but they are self-similar across scales. So what are these fractals? Fractals, not fraggles and not factors. Almost like a combination of the two, fractals. Because I was thinking fraggles, like Fraggle Rock, and then factors, which is a math and science thing. But these are fractals. They are essentially created by repeating a simple process over and over and over and over and over and over and over in a feedback loop. But they are driven by recursion. And so what we have are fractals or images of different dynamic systems that are the pictures of chaos. So geometrically, we have fractals that kind of show the existence between familiar dimensions. So fractal patterns tend to be very familiar to us, and because we see lots of different fractal images in nature. So we've got trees, and we've got rivers, we've got coastlines, we've got clouds and seashells and hurricanes. So we have all of these different things that come together through what we would see as kind of like chaotic situations, but they still tend to form these types of patterns that we can kind of see, which is pretty cool. The other thing we need to talk about, attractors, both strange and non-strange. Just be a woman on the internet and you get both. Ba-doom, there you go. That was my attempt at humor. Chaos is the natural order of things. You can't say it is chaos just because you don't understand the model. Well, we're going to talk about the ingredients of chaos here in a little bit. So attractors essentially are a set of numerical values in a particular dynamic system, where these systems tend to evolve. So systems do tend to evolve and move and change over time. And the attractors are kind of a set of numerical values associated with that system. Now, when a system value gets really close to the attractor value, it remains close even if the system is slightly observed. So what does this mean? What does it mean? It's like kind of mind-blowing. So sometimes we have to like take a minute and digest and process everything we just heard. And you're like, okay, here's the thing. Here's the thing that happens. All right. So complex systems. Complex systems sometimes appear too chaotic. Yet they run through their own cycles. So even though oftentimes these situations are rarely duplicated, a strange attractor is representative of a system that runs from situation to situation but never settles down. So they do have their own kind of cycles involved in that. Calling chaos the natural order doesn't make sense. How can you distinguish order from chaos? Chaos is a type of order. But you can get order from chaos. And that is where we can kind of lead into information theory. Because technically speaking, the universe is going to bits. It's absolutely going to bits. But how is it that we have order persist in regard to the fact that everything is going to the chaotic state of energy? You're looking at the chaotic state of energy known as heat. Heat is the most useless form of energy. It's, you know, it's completely useless other than keeping us warm. And a lot of energy is lost in our cells through heat. But yet, here we are, still in an organized state. And so the fact that we remain organized in a universe that's constantly trying to just go to bits, and it's steadily being ripped apart, going to bits. It's eventually all going to break down. We still have some form of order, and that comes to us through what we would call information theory. So, The Touchstone of Life, that is the book that was in my head. If you're curious about biological systems and how they utilize information theory in a state of chaos, and how we can kind of take this chaos in a way and form it into something useful, we can store energy in the form of information. And that's how we're looking at, for instance, genetic code, this sort of thing. Whew, that was something that blew my mind when I learned that in physical chemistry, learning a little bit about information theory and how that's utilized in order to generate order from chaos. So if you haven't checked out that book, that is a really cool book, Touchstone of Life. I will find, I think his name is Lowenstein. I think it's Lowenstein who wrote that. Very good book. You should totally check it out if you haven't. But things do run in their own cycles, even if it's chaotic. But there are cycles involved. Climate change, yes, climate's a good example. Ooh, fractals, rounding numbers, chaos theory, yes. I'm scrolling through. I'm trying to catch up on everybody's messages. Heat as an observable part of entropy. Yes, heat is an observable part of entropy, and the most useless form of energy that we have. Tell me that in my Minnesota winter. Yes, here we go. So I am caught up on our messages. All right, so here is a picture here. Here we go. Hello, our different types of attractors, our patterns in our cycles. We have a strange attractor over there on the top side, and the strange attractor still seems to find, it has cycles, but it doesn't actually settle down. Now when we look at it this way, it kind of looks like the circles are all weird, but if you turn it around, it actually does look like a set of butterfly wings, which is pretty freaking weird. Then we have the point attractor, kind of like a black hole, where you have a particular singularity in the middle, and then you have all of the swirls around it. Then you have the torus attractor, which kind of looks like Stargate, doesn't it? And then you have your basic cycle. But all of the attractors still have some sort of cycle attached to it. But the thing is they all go through cycles, but strange attractors, the ones where you have ones that kind of fall closer to that value, they don't settle on a particular spot. They never just stop at one pattern. They keep going. That's where we're talking about strange attractors. Man, this is breaking my brain today, guys. It's okay, it's not. I'm actually finding this inherently fascinating. So an interesting thing with keeping science interesting with a Mel. So an interesting thing about all of this. You know, I think one of my favorite quotes, I can't think of who it was one of the father of quantums, was like, if you think you understand quantum, then you don't understand quantum. Kind of similar to what Einstein says here. As far as the laws of mathematics refer to a reality, they are not certain. And as far as they are certain, they do not refer to reality. So we kind of have to keep this in mind when we're dealing with the fact, because you have so many different variables that can change at any point in time. And this is kind of what chaos theory thrives on a bit. So it's inherently interesting in that. Chaos theory does give patterns to randomness, but it has to accept the situation that you're going, the more variables you introduce and the longer the time frame, the less likely you're able to predict certain events, if that makes sense. Which is kind of weird sometimes. You're like, oh my freaking gosh. Oh my gosh. Gosh, golly darn it. Whatever they call it, you know. That's not what I wanted to do. I clicked the wrong button again. Alrighty. So, this is what I wanted. It's so funny. It's like, again, chaos theory. Too many factors. Too many irons in the fire, Mel. You know? If there are more irons in my fire, if I have more irons in my fire, I am less effective. I do know that, although I tend to get entirely more focused. Interesting thing, anytime I drink alcohol, I get way better at video games, and it ticks off all of my friends. And I'll be playing like Rock Band, and they're like terrible at it, and I'll be like, I'm going to Phil Collins this. Give me something to drink. Give me a microphone, and I'll be playing that drums, and I'm just kicking butt, taking names on expert, and people like, how do you do that? I'm like, man, I don't know. You introduce a new variable, for whatever reason, something else completely happens that you wouldn't expect. It's strange, but that's kind of how it works, which is also pretty freaking cool. So now we are getting in to the cool stuff, the butterfly effect. So we mentioned the computational weather dude who came across this idea regarding small changes that can affect on a huge grand scale. So the butterfly effect. Can a butterfly's flap of a wing cause a tornado in Texas? Well, the butterfly effect grants the power to cause this to happen. Now, this idea doesn't mean an instantaneous tornado will happen with the flap of a butterfly. No, it may take a very long time. But it introduces this idea that there's this very real connection of small things with large things. This connection between the influence of the two. The small things have an influence on the large things and vice versa. Now, if this butterfly had not flapped its wings at just this particular point in space and time, this tornado would not have happened. Now, another way to explain this is that small changes in the initial conditions of our lives lead to drastic changes in the results. And we see this in our daily lives, which is actually kind of inherently cool with that. You'll be like, if I hadn't bought this coffee at this particular time. Another example here. I was driving down the street probably a couple months ago. I think it was back in July. Horrible storm outside. I had been late, was held up somewhere else at a different traffic light, turned, start driving down the street. This truck that was behind me passes me, starts speeding up, hits a pothole filled with water, ends up slamming into a van, and it ends up turning around. I witnessed this accident. Had I been a little bit sooner, I might have missed it altogether. Had I been a bit later, I would have been stuck in the line and not been involved as a witness. But little things like this completely changed my afternoon. I had to go on and do a show later, and I was on my way home to do this particular show, and it shook me a bit, shook me quite a bit. So it's pretty interesting how this goes. Another example I like to point out. Chaos theory can just kind of blow your mind. Randomness refers to singular events typically, whereas chaos refers to a group of actions, a system. Chaos has to deal with systems, yes. Chaos can delve into randomness a little bit, but chaos theory more explains it, and mathematically, we'll get into the maths of this, more mathematically about what factors are involved in order to dictate randomness. I mean, as far as like chaos, what qualifies a system to be chaotic. And we can look at that. I'm trying now I'm kind of going on like, how do we see chaos theory in our lives and how different components and factors have an effect. Even small changes have an effect over the end result. So, one example I like to point out is when Seth MacFarlane, the Family Guy creator, missed his flight on 9/11 due to being out late the night before, and his travel assistant put the wrong time on his calendar. It put his flight leaving as 10 minutes later than what it was. And he had been out late, so he overslept. So two small variables drastically changed the end result. Had he been on time, we would not have Seth MacFarlane right now. So I'm going, and I have a video clip, so I apologize in advance for the next video clip as it contains Piers Morgan. So, sorry about that in advance. So here you go.
There you were. You were booked on the flight, I think, from Boston that hit the South Tower. Mm-hmm. And you didn't get on it. Why?
A combination of two things. I was giving a lecture at my college the night before and went out with some of the faculty afterwards and had a few pints. And
so you got drunk?
Yes. And coupled with the fact that my travel agent had listed the flight on my itinerary as leaving 10 minutes later than it did. And I was generally late for flights. I'd missed a lot of flights prior to that, so it wasn't like it was anything crazily out of the ordinary. But I got to the counter and I said, yeah, I'm booked on flight 11, and the one behind the counter said, sorry, you're too late. They just closed the gate. And I said, all right, well, I'll take the 11 o'clock. Went into the lounge, fell asleep, woke up about 45 minutes later to a commotion, and the first plane had hit, and sat there and watched the second plane hit, and they announced what flight it was, and I turned to the guy next to me and said, my God, that was the flight I was supposed to be on. I was late. I missed it.
I mean, what an incredible thing to realize has just happened to the plane you should have been on.
Yeah. I mean, there was that wonderful unity that we've since completely abandoned. I've never felt more than when I was standing at the bar at 9 o'clock in the morning and saying to the bartender, hey, can you pour me a shot? And he's like, yeah, here you go, it's on the house. And that feeling that must have been what our grandparents felt during World War II, where this is, in that moment everything was, we're all the same. But I'm not a fatalist. I was not shaken to the core in the way that I changed my whole outlook on life, mainly because I had missed planes before, and coincidences do happen. I mean, a day before that incident, I could have been crossing the street 5 minutes earlier and gotten hit by a car and never known that I just missed it.
All right, so so the video is lagging. Yes, I have like several chats that are popping up. Plus, I'm also, you got to keep in mind, I stream to Facebook, YouTube, Periscope, Twitch. And so I have all of these different chats that pop up on here too. So trying to catch them all. And sometimes they time out, so I have to fix the chat. So I'm trying to go through and catch up on everything. So this is a pretty hefty topic. So Seth MacFarlane, because of two small things that affected his getting to the airport in time, he would have been on the plane that would have, the Boston plane, the Flight 11, I believe, that hit one of the Twin Towers, and we would not have Seth MacFarlane now, which is actually kind of really sad and upsetting to think about. It was unwatchable. I am very sorry. So I'll put a link to where you can watch that video a bit later. So essentially what he was talking about is all of the different things that happened that led to him not getting on the plane. The main thing being he had been out late the night before. It's probably a little bit hungover. And then his travel agent had put a 10-minute delay on his calendar. So so these two factors changed the trajectory of what was going to occur. that plane was going to crash into the thing, but different factors, you know, this is kind of what chaos theory is. So these small changes affected the result of him. And that's kind of what chaos theory explains. You can have a couple of small tweaks here and there that can cause a substantially different result than what could have happened. And so that's kind of what we're getting at when we look at chaos theory. So let's kind of branch into what we talk about. So when we're talking about the butterfly effect, this leads us to the idea of sensitive dependence on initial conditions. Okay, but the vid, well, at least the audio is okay and you could hear that. All right, so that's good. Overtaxing my bandwidth. Maybe. I have the highest amount of bandwidth I could possibly get for where I live. As far as like upload speeds. I can't get any faster. Hello, hello. Get me fiber optic cable. So the butterfly effect leads to this idea. And these small little changes can affect a larger scale, even to detriment and chaos, you know, just horrible detriment to a degree, or completely avoid that altogether. So this is what we call sensitive dependence on initial conditions. Now let's consider this quote from Simon de Laplace in 1820, and I probably said his name wrong, so I concede that in advance. I'm very terrible with names. Anybody who knows me knows that I'm not very good with that, so I do try. So here's his quote. Given for one instant an intelligence which could comprehend all the forces by which nature is animated and the respective positions of the beings which compose it, if moreover this intelligence were vast enough to submit these data to analysis, it would embrace in the same formula both the movements of the largest bodies of the universe, classical mechanics, and those of the lightest atom, quantum mechanics. To it nothing would be certain, and the future as the past would be present to its eye. So this was Laplace in 1820. So if we're breaking this down, what he's essentially saying is if we know the initial conditions of a system with enough accuracy, we can effectively predict future behaviors within that system. Now, this isn't really going to work in every single case, but it can be plausible for simple symptoms with only a few variables that are not affected by noise, which is what we also call outside influence. Hello, everyone. Hello. So let's kind of dive in a bit deeper. Off and on. Uh-oh. So let's dive in a bit deeper. But even for simple systems, I am tripping over my words today like my shoelaces are tied together, man. Let's talk about Poincaré. He enlightens us a bit with his thoughts. If we knew exactly the laws of nature and the situation of the universe at the initial moment, we could predict exactly the situation of that same universe at a succeeding moment. Now, but even if it were the case that the natural laws had no longer any secret for us, if we understood all of it, we could still only know the initial situation approximately. Now, if that enabled us to predict a succeeding situation with the same approximation, that is all we require, and we should say that the phenomenon had been predicted, that is governed by laws. But it is not always so. It may happen that small differences in the initial conditions produce very great ones in the final phenomena. A small error in the former will produce an enormous error in the latter. Prediction becomes impossible, and we have the fortuitous phenomenon. Now that's Poincaré and his particular thoughts about it. So let me catch up. In one way, chaos theory is personified in our daily mundane delays, foibles, or errors that destructure our plans. Yes, that's one way to think about it. Yes, the video is a slideshow, but you can hear everything. Okay, I don't know what's going on with my bandwidth. It's weird. All right, so here we go. Now we're moving over to something you guys are familiar with. Life finds a way. So here's a film example of sensitive dependence on initial conditions. This is the water drop scene in Jurassic Park. The drop could roll anywhere down her hand, and this clearly has a big influence on the future of the drop. However, the sensitivity to initial conditions only arises for one particular case. If the drop starts on one side of her hand, the sensitivity disappears and is left with how it rolls down that side of her hand. To describe this motion as chaotic, we would require sensitivity to the initial conditions for a wide range of such conditions. Why we need dimensions? Yes, we do need dimensions as well. But even then, not only do we need dimensions, but we also need to understand potential trajectories. So now we're getting into math, guys. Woohoo! Or, math. No, not the math. Video sync back. All right. Now we're getting into math. If we're looking at math, or maths, if you are overseas and not American, maths. Chaos involves an exponential divergence of trajectories. A trajectory in this case is defined as a particular way in which a system might evolve. So remember, we were talking about attractors and those values and how a system tends to evolve towards an attractor. And we have strange attractors and non-strange attractors. Then we have the patterns that eventually form as pictures from chaos when we see these cycles come on out. Jeff Goldblum, yes. Now, if a system is chaotic, then two trajectories that differ by what are delta x0, and their initial conditions will, after a period of time t, differ by delta x times t is equal to delta x0 e, and then we have this little, what I usually call it the absorbance, because I'm a chemist. That's what we use to represent absorbance, but that's not absorbance in this case. It's t. So this particular, what I would call, it looks like it is an alpha. It's alpha. Is called the Lyapunov exponent and must be positive for chaotic behavior. And so note that the future behavior of a chaotic system is predictable, but only if the state of the system is known to infinite precision. So that's not really possible. So in practice, this is never possible. And so any particular real prediction is useless after a certain period of time, because after a certain period of time this is going to change. You can have different variables affect it. And so when we're looking at, for instance, here we got the pendulum case, the initial pendulum before we add the second one is always predictable. You notice that initial pendulum can swing back and forth, and we can calculate that. We add the second pendulum to it, and this is where we start to see the chaos and the different variables that are involved with it affecting its movement and its trajectory. Sorry, I have a bug flying around here. So what constitutes something as chaos? Yes, some of the tech glitches are just getting impossible. I don't know what's going on, so I'm really sorry that that's happening. Even the audio keeps freezing. Man, I don't know what's going on. I'll have to call my internet service provider and see what's going on. Your audio is cutting out now. This is weird. All right. So apologies for that. in order for something to be chaotic, it has to have 3 degrees of freedom. So these 3 degrees of freedom are at least the 3 different variables. So a simple pendulum has only 2 degrees of freedom. Yes, the video will be posted on YouTube later. It's lagging now. That sucks. I'm sorry. It's terrible. Yes. So a simple pendulum has only 2 degrees of freedom. The state of the system is easily described with that top pendulum moving back and forth by its position and 1 velocity. But it's too laggy to watch. I'm sorry. Adding a period driving force adds another degree of freedom and another variable to describe the system at a specific time t. We need to specify the phase of the driving force at the time. Hello. So making a single pendulum to a double pendulum adds 2 degrees of freedom, that the position and the velocity of the second pendulum, thus bringing about the chaos. This is how the chaos comes about. I don't know why it's lagging so much, so I'm very sorry that's happening right now. So hopefully this will stop. Lagging stinks. We are the best and the crappiest at the internet. You're right, we are. Okay, so hopefully if I've removed all of this on the side, I can talk a bit more about it this way, maybe with less graphics, so it's not so laggy. Maybe that will help. Let me see. What was I going to talk about next? So the second thing that we got to think about with no difference when turning off chat. That's weird. Okay. So the second thing we got to think about is there must be non-linearity in the system. So when we're talking about a linear system, all the variables, position, velocity, pressure, all of these things appear in the equations to the first power or not at all. So crap. I'm sorry, guys. I'm sorry that it's just buggy and laggy. So in order for something to have chaos, it has to have 3 different degrees of freedom, 3 different variables, and it has to be nonlinear. So when we look at the ideal gas law, PV and RT, it's an example of a linear system with gases. We increase a certain variable and we expect others to increase and decrease. So if we kick that particular ideal gas law, the linear system, if we kick it twice as hard, then the response will be twice as large. Now, in reality, all physical systems are nonlinear at some level, and linearity is only approximation. And so, for me, in chemistry, you have to consider when you're using a particular instrument, you're going to lose precision at some point. It's going to lose linearity. So once it loses linearity, you can't use that particular data if you're trying to determine like the concentration in a particular solution. So once it loses linearity, it's useless to you in regards to determining the concentration of a particular thing in a solution. So that's where you get into the chaos. Why did it lose linearity? What other variables and factors were involved with that? So we kind of see that in science to that regard. So when we're looking at, where are you guys at? Right here. All right. Hopefully it's working out a bit better. So what about evolution? What about evolution? What are we doing with that? Networks have chaos too, hence the current stream. Chaos. I have no idea what's affecting the lagging. No clue. Nothing else in my house is hooked up to anything right now except this stream. But hey. So now, what about evolution? How do we see this in the natural world? Is this a thing? Yes, it is. Rosen in 1991 stated, the natural evolution of quasi-isolated systems should be analyzed by considering the evolution process as a sequence of states in time. A state is the condition of the system at any time, and this can be either discrete or continuous. Now, at any time, we can consider the system state as the initial conditions for whatever processes follow. So when we're looking at evolution, we're looking at all of the different aspects of things that can occur. The chat isn't lagging, nor the audio. Okay, well, maybe the video is, and so sorry about that. But, so when we're talking about evolution, how things can change over time, we expect things to change, and we expect to see changes, but all of the different factors involved can determine the long term. So when we're looking at species, what would have happened if an asteroid didn't hit the planet? We would have still had dinosaurs around, and people may not even be here. It's hard to know. So chaos theory kind of takes into consideration, we look at natural selection as a perfect example of that. We know that things can change and things abide by the laws of physics. We have gravity, we have all of this other stuff, but different things can happen, and sometimes it just cannot be predicted. So what happens if that asteroid nudged a little bit to the left as opposed just coming right in on the planet? We'd still have dinosaurs here. We'd likely, or maybe not. Maybe there would have been like an evolution of a type of bacteria or virus that wiped out the dinosaurs. It's hard to say, but all of these different little small things can affect and have a drastic change on the larger group of stuff. So that's kind of what chaos theory explains. It helps us understand that we need to expect the unexpected, and the more information that we have about the initial conditions of a system, the more likely we are to actually predict. But in all intents and purposes, any actual real predictability is going to rely heavily on how much information you have about the different variables that are affecting a particular thing. And the longer it goes, the less accurate your prediction is going to be. So that's kind of what we're getting at when we're talking about chaos theory. So evolution, what is going on? So evolution, kind of to wrap up what I just said, evolution is driven via natural selection. While we can always expect a response from a stimulus, especially in living systems, there are always many possibilities. However, the initial state is always going to be the determining factor for the long term. Now, as the state changes, the responses can and will change. Chaos theory tells us to expect the unexpected, but we can predict if we have sufficient information. Newton's laws describe classical mechanics. We expect objects to remain in motion unless acted on by an outside force. This is predictable. However, the trajectory of where we are going can change if we have more than two variables. We can destroy ourselves as a society and a species the more variables we put into the equation. And there are responses that are factors that breed chaos. Life finds a way as we can organize the chaos through information, thus information theory, but that is another talk, now isn't it? Oh my goodness. So, life finds a way. So it is actively used in biology. So one particular website, I won't pull it up right now, but you can check it out. You can Google Scientific American and talk about chaos theory to revitalize fisheries. So this particular scientist went through and decided, I can probably, you know what, I think I can probably pull it up. Here it is. I don't know if you guys can see this or not. I think it's right here. Hold on. Life finds a way. Let's see, let's go to the big monitor. All right, so here is the article, if you haven't checked it out. Using chaos theory to revitalize fisheries. There are fewer fish in the sea than ever. Complexity theory argues mathematician George Sugihara provides a counterintuitive way to revitalize the world's fisheries. Now, this was posted in 2009, so it's about 9 years old. But essentially what they were looking at is a few decades ago, here it is right here, a few decades ago, after the Great Depression, the sardine fishery in California was suffering from a similarly devastating collapse. So what they did is, a few Cassandras might have warned of trouble in each case, nobody could have predicted exactly when each collapse would come or how severe it would be. So this sardine collapse puzzled fisheries experts. Some blamed overfishing. So what they did is this mathematician and theoretical ecologist at the Scripps Institute of Oceanography analyzed the data and came to a surprising conclusion. Both potential explanations of the sardine collapse were wrong. So this was published in Nature. He says a 500-pound fish in an aquarium, feed it more and it gets fatter. Feed it less and it gets thinner. The population of one is stable, but put 1,000 half-pound fish in that aquarium and the food shortages could result in deaths of hundreds because the small fry have less stored body fat and therefore cannot ride out a short famine. So he goes through and he uses chaos theory to kind of talk about why it is that these particular fisheries were collapsing. This is something that is actively used in biology. I'm not showing slides at the moment. I was just posting a picture of an article from Scientific American, and it's titled "Using Chaos Theory to Revitalize Fisheries." A really cool article if you have not checked it out. What if the cat refused to go in the box? Ha! Ha ha! You know what? You can't put the cat in the box, you know. Schrodinger. That's one against you, man. 1 for the cat, 0 for Schrodinger. Right? So I'm wrapping up chaos theory because everything is going nuts on this particular live stream. Hopefully what I can do later, YouTube should fix up any kind of issues after it posts it as a video. So I will investigate what's going on with this. It's weird how sometimes things happen and I don't always get what I expect in the end. So that's strange. Nudge theory, like where they put pictures of a fly in men's urinals and made men pee more accurately. Oh my goodness, that's funny. You guys are goofy, man. I love it though. I have lots of sources and I know you can't see all these. But I put them on my website, so that's all right. Go check them out later. I'm going to take a moment to thank my patrons. Thank you, patrons, for helping me out, man. You guys are awesome. Tony, James, Lauren, Jen, Carl, Melanie, Patrick, Daniel, Stephen, Paula, Tim, Carrie, Cersei, Keith, Duke, Andy, Zachary, Tony, Bo, Stephen, Sarah, Chris, Graham, Dragnot, Godless Iowan, Jennifer, Corey, and Heavy. Thank you for helping me keep the lights on. Thank you for contributing to my work here. I'm branching out and adding more shows. I'm working to do more outreach within my community. I've applied to NASA Solar System Ambassador position. Hopefully I'll get that. It's entirely voluntary, but that will also open up additional resources from NASA that I can share with you and others. So that's kind of the direction of my work. I'm currently working with Katie Paulson from Pathos to generate a new show called BS, Bad Science. This week in BS, Bad Science, hopefully will be a once-a-week show as well, where we will talk about the latest and greatest in bad science. And so I'm going to have Peter go for it, make me a new intro. And so I'm working with him. You guys help me keep the lights on, and I really appreciate that, and it means the world to me. I do have a lot of irons in the fire, so I appreciate your patience while I'm trying to sort out all of the different things and how to organize that better so I can provide more content on a regular basis. Plus the new job, I'm settling well into that, so that's helped as well. Where can you find me? ScientistMel.com, Patreon.com/ScientistMel, YouTube. Please like, share, and subscribe. I still don't have enough views yet for monetization. So please feel free to have a ScientistMel marathon just somewhere in the background on your TV at work. Any of those things. It's all safe for work, so you can always have it playing in the background there. If you miss a live stream, you can always listen to it later. So thank you guys for being a part of this show with me. This has been like super fantabulous and awesome. And I appreciate you guys being here. You always make each Saturday special for me. You know how? By just your being you. That's Mr. Rogers. I love Mr. Rogers. Oh my goodness. Poor cats. Oh man, you guys are funny. I think I've missed out a bit on what we're talking about. But this has been the science of chaos theory. Woohoo! Schrodinger jokes are always fun. Words are hard today, aren't they? Thank you guys for being here. I hope you've enjoyed this. This has been absolutely a blast and a lot of fun for me. And I'm super glad you guys picked chaos theory because I learned a lot of stuff today. My notifications browser. Do I have a notification? I don't have a notifications browser. I don't have any of that. I don't have a notifications browser. All I have is just the one that pops up on from your talk on my stream. So it's, yeah, so this is a little over an hour today because see, this is the only one I have is the chat that shows up. I'll see if I can find a better way to organize my stream to where it's not so problematic and see if I can't sort that out. Because I'm not certain what's going on with this. Why did I choose beryllium as my symbol? Ditching the traditional lithium? What? Somebody, are you talking about my logo? Are you talking about my logo? The Science Hub? Is that what you're talking about? Somebody drew that for me. Well, I'm glad you guys had fun today. And, you know, sending you hugs as well. Squishy science hugs. I'm going to go see Venom today. Woo! I'll let you know how it is. I'm going to watch it on the IMAX. We are Venom, you know, so maybe I don't have a scary mask to wear. I just have my face. So I could just wear my face, I guess, and walk around and say, we are Venom. Yes, we do got to do this again. Less internet chaos. I like dad jokes. I tell them all the time. So guys, please do like, share, and subscribe. Retweet. I also make little 1-minute videos, teaser videos for my shows, as well as little informational 1-minute videos. What I'll try to do is go back through and make some ScientistMel shorts. I'm off all next week, and I will be in New Orleans. So if you're in New Orleans, hit me up. I'm doing a live stream with Monty, and he has a show that he's going to start doing. I think it's on next Thursday, and I will be a regular appearance.